even if there's friction involved all across the string?
Friction meaning
Like on the, yeah, right there.
like on the pulley?
Could that change the tension of it at any point of the string?
The friction,
Because if not, it's just equal everyone's string, right? Tension?
yeah, the friction shouldn't matter if it's not moving.
Okay.
So I think that would be the same case. For rotating bodies, it's even a little more complicated. So I don't want to say too much.
Okay.
We'll assume it's friction. Are there any questions on that? Let me give you one more. Okay, so this is the same situation. I'm going to do a different thing. Now I'm going to have this situation. And just imagine that these are hanging up like that. If you think it's a trivial, it'll get a little harder in a second. So this, I'll call this T3. I want you to compare T3 and T1. Are they equal, greater than, or less than? So it's the first situation with the third situation there.
That's just a pulley hanging from the ceiling.
Yeah.
Okay.
Yeah. Support hanging in the ceiling, nothing accelerating there. All right, give me another 5 seconds. This vote was pretty one-sided, so I'm going to spend too much time on it. Okay, I'm going to stop the voting now. All right, looks like most everybody said C is correct, so they're the same. For the same reasons, I'll be right diagram, we get the same thing. One more situation. Okay, so now in this case, there's it's just tied to itself. And we want to determine if that's the same as the first situation, if it's less or more for the tension. You guys a little bit longer for this one. If you want to just draw a quick free body diagram, it might help you. It's not a very complicated free body diagram. Nothing's accelerating here, so it's actually pretty straightforward. Okay, take another 10 seconds. If you haven't looked in yet, or if you're going to change your answer. Alright, this one's a little split in both. It's actually pretty close. Nobody really said A, but a lot of folks said B and C. So I think the best way is just maybe discuss with your neighbor, take like 15 to 20 seconds. Try to convince them of your answer. We'll come back to the class. We'll revote.
Did you put, what'd you put?
I think I changed from B to C.
I have mine at B
Or
because
it's
I
changed
wasn't
from
sure about
A.
less or greater than, but I figured there's the same string, but two different parts, so they're each taking half the weight of the block. So would that mean there's less tension on each of the individual sides, right? That's what I would think. Then if they're equal,
But what if the block is equal to two of the blocks on the left?
well, it says A, so I'm assuming it's the same weight.
True.
But I would think that it has two things. It has two anchors that it's holding from, so I think it'd be half. So you changed it to C?
I changed it to C. And the reason why, yours sounds pretty convincing, but it's because the tensions are going to be this. Well, you're not comparing that tension to that one.
These are weird, man. I'm not sure.
T1.
Because the mass.
I'm actually not sure. A lot of this is like really counterintuitive. Like you think it's one way, and it's totally different way.
It is one string holding one block.
Okay, go ahead and read like
It could be either or. I'm not sure.
Oh my goodness. Which one?
Wait one more time. Okay, I'm gonna stop the volume. And it's a little more one-sided now. So everybody who said A before is obviously doing so. And then there's a lot more B's and a little less C's. B is correct. If you just draw a quick free body diagram. For A, we have T1 going up. And then for B, we have two T4s going up. Nothing's accelerating, so when I use Newton's second law, in this case I'll get T1 minus W equals 0. In this case I'll get 2T4 minus W equals 0. So T4 equals W over 2, so it's got to be less than T1. So in that case, the tension in each of those wires is half. And that makes sense. I mean, there's a reason that the speaker up here is hooked up by 2 of these strings. Because each of those strings only has to hold half of the weight. So that's why they hold things up with more strings. So in each of those it has tension of whatever the tension is with 1 divided by how many strings you have. Okay, so the answer is B. And a free body diagram can just get you through that really quickly, which is why it's important to draw it. And but I made this another meeting. I want to show you this. It illustrates hopefully why the free body diagrams are just so critical. And not only the free body diagrams themselves are making important. Every time I do a problem in this class, I'll make sure I do that just to be really consistent. And I notice that whenever I'm working with students and they seem to have a little problem with it, usually I'll go back and see that they've skipped so many steps. So try not to skip these steps. Even when it seems trivial. In this case, it may seem trivial, like I do this in my head. Well, if you write it down, you're not going to get it wrong, even if you can maybe do it in your head. And in some cases, it will dispel some misconceptions that are very prevalent. One of those misconceptions is this misconception, which says that Fs equals mg. That's not always true, so we'll do some problems where that's not the case. And you'll see that in the free body diagram, it'll be very evident why it's not the case. Let me start out with a couple of problems that are static problems, which don't have any acceleration. So let me do this one on the phone. I want to go on that design. Let me try that one first. And I did it yesterday in discussion section. I'm going to do it a different way today. So if you saw me do it yesterday, this will be an added practice. And then the angle is given at 40, 50. And this thing says that it's not accelerating. Okay, so all the accelerations in every single direction will be 0. And we're going to solve for T1. Okay, so what is T1? Now, when you do these problems, you always want to draw a free body diagram for every single free body inside the situation. In this case, it's a little less evident that this knot is a free body, but because there's forces coming out of it in different directions, I'm going to call that a free body, as is this mass diagram. And that mass is given as 5 kilograms. So, separate from this, you want to draw something on the side that just has each of these masses. So here's the mass free body, and it has 2 forces on it, weight going down and tension 3 going up. And then this knot over here, so draw the little circle, has 3 forces upon it, tension 3 pulling down and the tension 1 and 2 pulling in oblique angles. Once you have the free body diagram written down, you always want to make it so that there's nothing else on there. Don't even draw like the ceiling or anything else. Just draw the body itself and any vector forces coming out of the center. And the next step is to define your coordinate system. And the coordinate system, you can use a different one for each one of these. So this one's obvious. I'm just going to choose like this because everything will be in one direction then, obviously. This guy, there's a couple ways to choose it. And so your coordinate system, the x and y always have to be perpendicular. And generally, if it's accelerating, you want to choose it so that the acceleration you expect it to go in is along one of the coordinate axes. So if you expect it to go down the ramp, choose that as your x, or your y. Don't choose it like this. In this case, nothing's accelerating, so the other method is to choose coordinates in which as many forces are lined up along the x and y as possible. And the nice thing about this problem is that this is 40, this is 50, so what is this angle right here?
90.
Right, so it's a right angle, so I would make my coordinate axis like this because it might save you some time. But if not, if you're not comfortable, you can do it like that. It's totally viable. I did it yesterday, so I'm going to do this one today. So I'll call this x and I'll call that y. Okay. Once you have the coordinate axes written down, the next step is to look for all the forces that are not in the direction of the coordinate axes and break them up into components that are. So let me write this down. So first one is free body diagram. Next one is coordinate axes. And the next step is to decompose forces into forces along the coordinate axes. So let me write. In this case, you already have two of these along x and y, so those are fine. But T3 is not, so you got to find out its components. And the point of this is that T3 is a vector, right? So we can always express it as a sum of other vectors. So this T3 points down. But it's the same thing as if I made a vector that goes like this, and then like this. Two vectors. And this is some components, and that's some components. And this I'll call Ty, and this I'll call Tx. So instead of writing this, I can write that instead. And these are useful because they go along the coordinate axes. But you do have to find out how to decompose it. So let me just draw this a little bigger here. And then whenever you decompose a vector, the component should be at right angles, and the vector itself should be the hypotenuse of a right triangle. And then make sure you draw your arrows so you know which way they're pointing. This vector points down, so it's the sum of a vector that goes this direction, and then goes this direction. So I can either go this way or I can go that way and then that way. It's the same thing. So instead of using that one, I'm going to use that one. I'll use two rather. And the only last step here is to figure out what the angles are inside here so you can actually find out what the components are because you have to do trigonometry to find them. So that may not be totally obvious. Maybe I'll just draw a line like this or something. Maybe that'll help? Yeah, let's try that. Let me make this a little longer. So that line up. So this angle here is 40. So what's this angle right here?
50.
That should be 50 because this is 90. So that's 50. And these are the vertex angles, or whatever you call them. So this has to be 50. So if I'm making a mistake, just raise your hand and let me know. Yeah.
Isn't there an easier way to do it? From T3, like along the diagram itself, over there, yeah, if you like make it T.
Oh, right here?
From T3, yeah. You go straight like that, and up, and then you follow it like that.
Oh.
That works for you, do that. Yeah. There probably is an easier way than what I'm doing. But anyway, however you want to solve it, it's pretty simple geometry. This is 50, so this is 40. I'll just call that 50. Just use it. Okay. I got an angle there. Now I can find out what these components are by just using trigonometry, simple trigonometry. So this vector, well, if I use cosine of 50, I'll have, I'll call this Ty is Tx. Cosine of 50 is adjacent or hypotenuse, so cosine of 50 is Ty over T3. Which tells me that Ty ty is t3 times cosine 50. And you can probably guess that this would be t3 times sine 50. Is there any questions how I got that? So I said the trick here to get those. Notice a lot of students, you guys are used to seeing that the x corresponds to cosine, which is true for like a circle and stuff like that, when we talked about decomposing like vectors in a circle. That's just for that one case. When you start drawing vectors in weird directions like this, x is not always cosine. So you have to draw the angle and then use trig and then make that consistent with other components. Now that we have this is it's easy to solve because all our vectors are going along the x and y coordinates. So once we've broken it up, the next step is to write down Newton's second law in every direction. And for each free body. Okay, so I have an x. Well, this one's easy. Let me write down that one first. And this is my mass that's hanging there. And nothing's accelerating, so I'm going to write down the sum of the forces, so I'll say for the mass. The sum of the forces in the y direction equals the mass times the acceleration in the y direction, which is 0. And that gives me, the sum of the forces is T3 pointing in the positive y direction, and W pointing in the negative y direction. So this has to be positive, it has to be negative. Which gives you that T3 equals W. That seems obvious. Okay. That's all we need to do for that one. There's no x components. Now for the knot, there's going to be two different components I have to work with. The x goes in some oblique angle like that, and I need to look at all the vectors in that direction. One of them is T2, which goes in positive x. And then the other one is this Tx, which goes in negative x. So I'm going to have T2 minus T3 sine 50. T2 minus T3 sine 50 equals 0. And then in the y direction, I have my y is going up that way, so I need to see all the vectors pointing in that positive direction, which is T1, and then the negative y direction is T3 sine 50. Did I mean to write cosine here? No. So I said that wrong. So T1 this way, and then T3 cosine 50. And you notice that because I chose my coordinate system wisely like this, the problem is trivial now. It asks you to find T1, and it's just given by this. And if you're not sure what T3 is, you have an equation telling you exactly what T3 is. T3 is W, which is mg. And it gives you mass and it gives you g, so you can calculate for that. Plugging that in there will give you this. That will give you T1 equals W cosine 50, which is the same thing as mg cosine 50. Now the way I did it yesterday, I did the same process, but I chose my axes like this. And it turned out there was this mess up equation we had to solve, which is fine. I mean, it's totally viable way to do it. I chose a smarter system this time, so it was easy. Is there any question on the problem at all? Yeah.
Wouldn't it be sine? Because if the string is massless, you can just point T3 straight up as the normal force. And then it would be the T3 sine of 40. Because it would be opposite of what I thought. Just pull it out.
No, I think that's what I think I have it. Yeah, if you still have an issue talking about the class, I think that's correct. Unless I had this angle wrong, but I think the angle is
No, if it's 50.
I know, but we need it to be on surface.
Sorry?
For a normal force, that we need it to be on a surface.
Yeah, for a normal force, it would have to be on the surface. So there's no normal force in this. Okay, any other questions on the problem? Yeah.
I'm a little unsure how to get out each little sign and which one's cosine. You go over that geometry.
Yeah, are you unsure how I got the angle? Or do you get how I got the angle?
I got how you got the angles.
Okay, so when I have that angle, let me just draw the picture a little bigger. I'm going to just draw this triangle here a little larger so you can see it. This is trigonometry, this triangle. Cosine of 50 is the adjacent over hypotenuse. And if I solve that for ty, I get t3 cosine of 50. Same thing. Are there any other questions? Okay, so the process here is the most important thing. I was very careful to do everything totally worked out. So free body diagram, coordinate axes, I do this for both of them. And then I decompose the forces. And when I wrote down Newton's second law, one thing I was very careful to do is that I looked back at my coordinate axis and I made sure that if I went in the direction of the coordinate axis, I made that a positive force. So it's opposite the coordinate axis of the negative force. It's very important that you don't just write these down in one. You have to use those every single time as you go back to the problem. And be consistent with how you actually made the coordinate axis. Let's do this one. This is this woman happily holding her suitcase. Now, technically, this is a friction problem. Excuse me, but it gives you the frictional force, so it's not really like having applied friction. So I'll talk about friction in a moment, but this one just kind of gives you the force anyway. So I won't worry about saying too much about the systematics of friction. It doesn't work at all. Not just that. Question says, a woman is pulling a 20-kilogram suitcase at a constant velocity by pulling on the strap at an angle of theta above the horizontal. So she's not really pulling it like straight like this, she's kind of pulling it up like that. She pulls with a force of 35 newtons. The frictional force between her suitcase and the ground is 20 newtons. What is theta degrees? So the first step is to draw a free body diagram. And the free body in question here is the suitcase. So if I just draw a little box in the suitcase, I need to ask myself, what are all the forces on that suitcase in every direction? Some of them are obvious, like the weight. The normal force that's keeping it up on the ground, so it doesn't go crashing through the ground. There's a frictional force, which whenever you have something moving, if it's already moving, friction will always point opposite to it, so it has to be going in that direction. And it's usually the F sub F. And then she's pulling it with a force as well. But notice that her strap is pulling up at an angle, so her force is not pulling straight out, it's pulling like this. And that's very important to draw the vector like that. These are always, angle dependent. And this angle is 30.
Not good.
Yeah, it's fine. It's 30 theta. And the question says, what is theta? Excuse me, the information you're given is that the frictional force is 20 newtons. And the force that she's pulling with, which I'll call force, I usually call it applied for like a force of pulling, or maybe a tension, you can call it that if you like. That's 35 newtons. And then the mass is 20 kilograms. There's a lot of information here. So once I have a free body diagram, I got to define a coordinate system. And the coordinate system here will be most obvious. I mean, she's pulling one this way, so the thing is moving like that. So you want to make that one your coordinate axis. And then the next step is to decompose all the forces that are not along those axes into forces that are on those axes. So this force is going in some oblique direction. You want to write it as a different force. That's the sum of two different forces. So it equals this plus this. Okay? So I'm going to decompose this force. Let me just write it right over here. And then you want to find out the missing size of this. It's pretty simple because it gives you the theta here. It doesn't tell you what it is, but if you know that number, you can find it. So if we just use trig again, this side is going to be, let's call it fx, and this is fy. If I use trig one more time, I'm going to have cosine of theta equals the adjacent side divided by hypotenuse. So it's fx over f applied, which tells me that the fx force is just the applied force times cosine theta. And then Fy is the same thing as the applied force times sine theta. Any questions how I got that? Straightforward. The next step is to write down Newton's second law in every direction. There's only one body here, so you just have to deal with the two directions in this one point. So for the x direction, you have this f applied cosine theta pointing in that direction, in the positive x direction, going back to my coordinate axis, and then this guy's pointing backwards. So I have f applied cosine theta minus f friction equals the mass times acceleration in the other direction. And then for y, I have a similar equation. Y, I have Fn pulling up, I have weight going down, and then what else? Yeah, force applied, the component of the force applied going up. So I have Fn going up, I have F applied sine theta going up, and I have W going down. Let's go back to see what we're looking for. So the next part, I didn't write it here. This really should be, look at the equation that has the variable you're searching for and see what you're missing. Well, both of these have theta in them, so let's look at the first one first. I have F applied, that's 35. I don't have theta. I have the force of friction, which is 20 newtons. I know the mass. The acceleration, do I know that?
Zero.
Zero because you're moving at constant velocity. So that's right up there. So acceleration is 0. Sorry, I should really write this over here too. This one is 0 as well because the box isn't coming up off the ground, or the suitcase isn't coming up off the ground. I should have explained that instead of just writing 0. And so in this case, I have everything I need because I have F applied and I have force of friction and I'm looking for theta. So cosine theta equals F friction divided by F applied. And you just plug in the numbers and it's straightforward. You don't even need that y equation at all. In fact, you don't even know a lot of you don't even need to know the mass. So it gives you some extra information. That's how you solve it. But it was very systematic. I broke everything up into different angles and directions. And it's well done. Now, if you look at this equation for Fn, this is a good illustration of how the normal force is not always equal to mg. If I rewrite this for normal force, there's no acceleration in the y direction, so I'm going to move these to the other side of the equation, and I get this. You could solve for this once you find theta using this method. You can find theta, plug it in here, and then you can just find a number for this. But you notice that this equals mg minus f applied sine theta. And this is not equal mg. And the reason is that the normal force, what it really means is that, I think one way to think about it is that it's a force of something holding something else up. So one way to imagine it is that if you had a very heavy box, like let's say I laid down right here on the floor, and somebody laid this heavy box upon me. And the force that I feel from that box is the normal force. That's what I got to push up so my chest doesn't cave in. Despite these pecs and these abs, his chest doesn't cave in. Now, let's say somebody else came over and wanted to help me out, and they just kind of pulled up the box a little bit. I would feel a little less weight on it, right? That's exactly what this woman's doing. She's pulling up a little bit on that box, and I feel a little less weight. So my normal force is what I normally would have been, how much the box weighed, minus however much you're reducing that load upon you. So the normal force really depends on all the forces acting in the direction that's perpendicular to the surface. And a lot of times it's just weight, but a lot of times it's not just weight. Yeah.
So for force of friction that you wrote over there, is it the same thing as FK, kinetic friction?
Oh, that's a good question. She asked, is this the same thing as mu k times Fn? Yeah, it should be. I'll go over that a little later. I'll go over that in a second when that's the case. Yeah, in this case it is. Are there any other questions on this problem? Yeah.
So if I use the second equation, do I get the same setup? Because I didn't use the second equation, I didn't get the same theta though.
You use this equation?
Yeah.
You solve for theta?
Yeah.
How do you know what this number is?
That's you.
So you don't know that. You have to solve for this using theta. Because this is unknown. Are there any questions on that problem? Okay, I got another conceptual question. So this would be a quicker question. I just want to see if this is a really tricky problem. It took me a while to convince myself to this when I first taught it. Let's see if you guys can figure it out. This is number 58 in the book from chapter 5. Yeah. So number 58 shows a guy who's like, he's in this like little, I don't know what this thing is called. It's like some thing. He's like hanging, and he's like pulling himself up. So it's like this thing is suspended from a tree or something, and he's hanging off here, and he's pulling himself up and pulling on the rope that's attached to this, and it's wound above when it's pulled. Right, does that make sense? So he's like trying to pull himself up by pulling on that rope. Kind of like these old window washers back in the day. What I want you guys to determine, I'm going to put a couple diagrams, and I want you to tell me what you think will be the proper free body diagram. And I'll call the tension this here T. So the first option has W and T like that. The second option has two T's like that. And the third option has a W and T pointing down. And another T pointing up. Okay, so all I want you to do here is just determine what you think will be the proper free body diagram to solve this problem. I didn't tell you the acceleration, but how would you do the first step? Just to try to figure out it. Take a minute to think about it. Just maybe put in a response, and then we'll come back into class and see if we can figure it out now. What would you do? Try to get your vote in the next 15 seconds. All votes in? You don't have to just yes or no. Okay, so this is a pretty close vote. It's really close vote. Yeah, talk this over with somebody, see if you can figure it out. Try to convince somebody.
Which one did you put?
I picked B
Yeah, me too.
because weight's going down because he's sitting on the elevator, the Buzon chair, whatever it is, and then you got the tension from the top, and then because he's pulling down on there, there's tension that's going up also.
Yeah, that's what I figured too. It's like it's the same thing as having two different ropes with the same tension on the box.
And there's no tension. There's no tension on the bottom.
Yeah, the
so.
bottom's loose, I think, so it's definitely not C. So yeah, I put B too.
But the tension is
This class goes till 7:50.
Yeah.
Okay, the voting is open, so whenever you think you can decide as a manager.
I'm not changing.
I don't think they're
Nope.
because he's essentially just pulling himself
And watch, it's probably gonna be the opposite.
attention.
Yeah.
But for me, it's that way.
So do you like the engineering one class?
Yeah, pretty cool.
This is always good.
But it made me down my spirits when she's like homework.
Yeah.
Really?
I think I'm gonna drop the class. Definitely.
Yeah.
Not because of homework, but because I need like the space between my last class and this week
Yeah.
homework.
Yeah.
Take like another week. But yeah, it's fun. Just listen to that thing talk about it.
It's a little more skewed towards B now. So B is the correct answer.
Yeah.
Let me explain why this is the case. Well, we know that, I mean, first of all, it's obvious that there's at least W going down and at least one tension coming out from this string. Okay, those are self-evident. The question is, how does this play a role in this string? And one thing is that he's pulling himself up on a string, so there has to be some force that he's pulling. The question is which way it's going. If you're not sure which way it's going, imagine, I guess, here's how I think about it. Imagine this is like somebody's long strand of hair. I think it's like his hair nowadays. Imagine that's like this is somebody's like really long strand of hair. He's pulling it down. He's pulling it down. Oh, you're pulling the hair down. So which way is that hair pulling his arm? It's going to be pulling the opposite way he's pulling it. So that rope is pulling his arm up because he's pulling it down. And he's attached to this whole thing. So this is going to add an extra tension going up. That's actually pulling himself up. Because he's pulling it down so because of their law, equal and opposite reaction pairs, it has to be pulling his arm up. So this is going to cause him to go up. And so in fact, the fact that he's doing this, if we solve this, we're just going to get 2t minus w equals ma. And so the tension equals this, which is m times g plus a. Notice that in the case where he didn't have this thing right here and it was just going up, somebody had to pull this thing up with the tension of this much. But because he's up, it reduces the tension by 2. So it's actually easier to pull yourself up than to have somebody else inside pulling you. Because there's two tensions that you're not only pulling, your hand is pulling up, but you're pulling the backside. There's two of those pulling you. Likewise, if you have like one arm pulling, if you kind of had this thing like broken, you have one arm pulling, one other one pulling up, it would be divided by 3 the same. But again, if you're not sure the way the force is pulling, think about how he's pulling it. And the fact that it's an equal and opposite reaction pair means it has to be pulling in the opposite way. So there's an extra T going up, in addition to the one that's on the crate itself.
Can you explain how the feet are equal?
Oh, why they're equal? Oh, because, that's a good question. Why are these tensions equal? Because this is all one string, so everywhere the tension has to be one. If it's taut, as long as it's not stretching, it's one string. What is it? Yeah. This is the same question he asked. The tension he's pulling up is the same because the string has the same tension everywhere. It's one string. If it didn't, it would slacken or it would like.
So by using a pulley and having more than one part of the string that has a tension, it actually uses less energy to pull himself up?
Not less energy, it loses less force.
Less force?
You know, what gets energy over time? Energy is the same no matter what. But the force is less. We'll talk about less.
Okay.
We'll do this problem again in a few years.
Okay.
Okay, so that's just conceptual question. Can you move on maybe from the book or something? Okay, I'd like to do one or two more problems without too much friction, then we'll go on to one of the friction. Number 55 in the book. It's a little trickier problem, but it's the same process. Sorry, number 50. Number 50. It's chapter 5, number 50.
50.
Okay, this problem is, it says 3 ballot boxes. This book is so weird. It's like the weirdest things. 3 ballot boxes are connected by cords, so there's 3 blocks. So these things are connected by cords over this frictionless pulley. There's no friction here, no friction on the pulley. And the masses of them are given. So this guy is A, this is B, and this is C. And mass A is 30. Mass B you also know. And then mass C you also know. And that's all in kilograms. And it's initially thrown at rest and it's released. And the question says, what is a tension in the cord connecting BC? So they call this tension T2, I call this tension T1. The question is, what is T2? And then part B will find out the rest. So what is the tension connecting it? So imagine holding this thing at rest and just letting it go. It's going to fall because there's some weight pulling it down. There's no friction. So you can imagine it's going to fall. So we don't want to be setting acceleration equal to 0 just yet. Now to solve this, the same process. I'm going to draw 3 body diagrams for each one of these 3 blocks, define the coordinate system, and then solve for the right Newton second law and solve for the unknown. Now here I'm going to be, I'll show you why the coordinate system, even in cases where it seems trivial, is very important. So let's do the free body diagram for A, B, and C. For A, I just have this block here. Now for A, there's only one force pulling on it. Yeah, just one force. So just this force pulling on it, just T1. This is just one string, so it has the same tension. This tension may not be the same as that. It has a two. So this guy just has one force pulling on it. And there's also the force keeping him on the track here, which is the normal force and the weight. Anything else? Now for B, there's only, well, there's a couple forces on here. So what are the forces on here? Just yell them out.
T1. T2. The weight.
And the weight. So he also weighs something. Despite being pulled down by C, he also weighs something. There's 2 forces.
Oh, yeah. Okay.
I should call it, sorry, weight B. That should be specific. It's not the same weight as that. Call it weight B. And then what about C?
T2. And the weight C.
Weight C. Are there any questions on the forces that I included today? If I'm missing any, why I know what them. So then the next step is straightforward. Define the coordinate system. For each one of these, you can use different coordinate systems, all the same, because everything's up and down and to the right. Okay, but make sure you write that down. Make sure you write this down and refer back to it whenever you need to. And And the next step is to write down Newton's second law for each one of these blocks. The first guy, in the x coordinate, I'm going to have all the forces in the x direction must equal the mass of block A times the acceleration of block A. And I'm being specific here. I haven't discussed how acceleration of these three different blocks are related. At the very beginning, you want to keep it all separate because you don't know if they're the same, equal, opposite, what. So at the very beginning, just make sure they're very distinct. Put everything with a subscript relating to what it is. And the only force here is T1, so T1 equals MA, AA. And in the y direction, it's the usual equation. Nothing's moving up and down, so that's going to equal 0. You say AA in the x direction for that guy. And so I'm going to have Fn minus WA equals 0. So that just tells me the normal force equals the weight. Okay, now for the second block, I only need an equation for y because there's no forces in x. V, A, B. We call it y. It's in the y direction. So sometimes these accelerations can get a little tricky with the subscripts, but it's better to be specific, even if it's a little fun, right? Now all the forces in the positive y direction are T1, the negative one are T2 and WB. So I have T1 minus T2 minus W sub B equals this. Any questions about that equation? And if we don't, this is not 0. This thing is going to start falling. It has a sign of 0, so we want to keep them non-zero for now. So this is our first equation we're going to use. Our second equation. This one won't come in much use. Let me go ahead and outline it anyway. And then for the last guy, it's, again, a straightforward equation. It's just T2 minus W2, which equals mass C times acceleration C in the y direction. And that's our last equation. Okay? And the next step, I didn't put it up here. Maybe I should put it up here. Relate accelerations for different objects. This is not always needed. In this case, it is needed. These things move as a system, so they're going to have the same accelerations all the time. If they didn't, there would be like a slack in the string. It would slacken or it might snap or something. So it's important that they move in the same acceleration such that the system moves forward. Now, what I want you to do is there's three accelerations here. There's A, X. There's AAX. There's A, BY, and there's A, CY. On your paper, just try to take maybe 10, 15 seconds. And I want you to write down whether you think these are equal, whether you think that the first one equals the negative, the second one which equals that, all which equal negatives of each other. Try to figure out what the signs are for these. Each of these is going to be plus or minus something in one of these, so we're not sure yet. So take a look at the coordinate system here and think about if you move this to the right, what would happen to each one of these accelerations, whether you're positive or negative? And try to find a relationship between all those accelerations. Take a few seconds to write that down, and we'll do it. And I'll do it on the board and see if you get it right. So again, I just want you to figure out the signs and then the equality.
What do you?
I'm not even sure I just wrote it down. So it's going to be negative and positive. So. Second two negative. First one wasn't.
Use a coordinate system.
Yeah, because they're all the same like that, right? So
does somebody want to tell me what they got for that? Maybe explain it.
I got the X subscript AX. I got positive.
Okay.
And then for A subscript BY, I got negative.
Okay.
And then I got negative for the last one too.
Okay. Does anybody want to dispute that? Good, this is right. So the reason that's correct is if you assume that this guy is going in the positive x direction, in the positive x direction, then these guys have to be going down, so they both have to be going negative. So he got that if this is positive, these two are negative. You could have also written negative, positive, positive, it's the same thing. All right, so what I'm going to do is I'm going to call this first one A. Call it A. That means this guy has to be negative A. That means this guy has to be negative A also. So whatever this one is, these are the same number, but they have negative signs. We know the magnitudes are the same because they're all loading as one system. All I have to do is determine the sign. That's the only hard part of this. And what I'm going to do is substitute those numbers back in here. So this guy's going to be positive A. This will be negative A. And then this one will be negative A as well. And now if you look at these equations, they can all be combined. The only unknowns here are T2 and T1. And in fact, this thing is only asking for T2. So let's try to solve it out. Yeah, it's asking for T2. So right here I have T2 equals W, T2 minus W2 equals this. I'm going to rewrite that up here. I'm going to have T2 equals W2 minus the mass of C times the acceleration. Well, I can't solve this because I don't know the acceleration. So I just have to figure out the acceleration. In that case, I'm going to plug this one into this equation. So I'm plugging in the second equation. That's the third equation.
Is that W2 or W2?
Right here?
Yeah.
W2. WC. Okay, so if I plug in T2 in that this third equation here, I'm going to have T1 minus this quantity minus WB equals that. Okay, so I'm getting somewhere because you see I have everything here in terms of A, and these are quantities I know. I know the weights of all these things. But I have to get rid of T1. So I can use the last equation for that. And T1 is just M1, MAA. So if I plug this in, and now I plug in the first equation. And T1 is MA times A. And if I just distribute these signs on like this, on the test, you should go slow with this stuff. Just watch your signs, because if you get tripped up on a long problem like this, if there's a long problem, then going back and finding the mistake is much harder than just taking a little extra time and not making a mistake or places you can avoid it. So just try to go slow with these things. Be very careful about how you plug in this stuff. Now here I have everything in terms of just A and stuff like that, so I can solve for A. So to solve for A, you want to put every term that has an A on one side, and every term without an A on the other side. So I'll move this one over here, and I'll have NA A plus MBA, I will that over, plus MCA. And then I'll move this to the other side. And this, what is this?
WC.
Sorry. Move those to the other side. WB plus WC. Which actually kind of works out to be a little cleaner equation. I just have the acceleration and the mass, the sum of all the masses equals, and I can make this G times MB plus MC. So the acceleration is MB plus MC divided by the sum of all the masses times the gravitational acceleration. Okay, once you solve for A, you can plug it back in here to find out what T2 is. So that's just a matter of plugging in numbers, getting a number, and then plugging that in there and getting whatever T2 is. So, okay, this is a long problem. But notice how even though it looks very complicated at the very beginning, breaking it down is very systematic. All you do is write down all the forces, and they're already in good directions, already next to one. So you write down the equations, and the only thing I think that was tricky about this problem was determining this equation. determining what these are, how the signs are related. That's the only tricky thing. And then once you put that in, be very careful about the signs as you do the algebra, so that you don't make any careless errors. And then you can just solve for it. And that's what the answer is. So then you can plug that in and find it. Alright, so I'm going to do some friction problems now. We do one homework. Before I do that, let me just give you a full demonstration of frictional forces. All right. Now, the thing about frictional forces is that they depend on what they depend on a couple things. They depend on what the applied force is, and they also depend on the motion. So, for example, when I mentioned has a heavy filing cabinet here, and this dude wants it because he wants to move it to some other location. So let's say he applies a force. Applied force is let's say right now. He can't move it. He's not pushing the part of it. And the reason he can't move it is because there has to be some other force opposing his action upon it. If there wasn't, he would accelerate it, because in Newton's second law, you have one force that's going to accelerate. But since it's not moving, there's got to be some force opposing it. That's that friction force. And that red force is friction, and the blue one is what he's applying to it. Now, what do you imagine would happen if you push a little harder, but still not enough to push it? What happened to the friction force? Yeah, it would increase to match it. Let's try this. So let's use general strength we have to integrate. Now I push this one. So he's pushing a little harder, but it's still not moving. Notice how the friction force matched his applied force. If I draw a free body diagram for this, I'll have this applied force, and I'll have the friction force. And if I just write down the equations of motion, this is zero because nothing's moving, which tells me that the applied force has to equal the frictional force. As long as this thing is staying put, the frictional force is going to match whatever you push. That's going to go up to a certain point until you push it harder. That's still not hard. Still not hard. So you got it. Let's try this out. Okay, still not hard. So now you see how this friction force is less than the applied force? There's a net force in the right direction, so it has to be moving. So he's gotten to the point where he's actually overcome the he's overcome the frictional force. Now the frictional force maxes out at a certain point. It's strong enough. And the way you can think about it, I think, is like imagine that you're beneath this file cabinet, you're like hanging onto it because you don't want to lose your files. So, and this guy's pushing it. And every time he pushes harder, you've got to push harder back to keep it from going. But you can only hold so much weight because your fingers are not as you don't have as much grip as him pushing. So at some point he maxes it out and his force overcomes the frictional force. And that value is given by what's known as so I'll call it the max. There's not really a name for it, so I'm just going to call it max static frictional force. And that equals this Greek letter mu sub s times the normal force. So the frictional force depends on the normal force, which makes sense. It depends on kind of how hard this thing is weighing down on the surface. But this is the max. It's not always that. So what I like to write is this: that the frictional force is less than or equal to mu s times Fn. Because that's the most it can be. Once it gets past that, it's going to break through that barrier of control. So why don't we do this? In this situation, why don't we find out what this max force is? What is the max force for this one? So what we can do is just draw a simple free body diagram and figure it out. The free body diagram will look like this. And I want to figure out what the maximum force you can apply before it actually breaks the barrier, before it gets it going. And that's just this mu s times Fn. And I'll tell you mu s, I think it gives you this up there. I think it's 0.3 inches. You're right there, it's 0.3. So that means coefficient of static friction when it's not moving. There's two different coefficients when it's not moving and when it is. When it's not moving, the coefficient is 0.3. So if I want to find out the max force, I'll just use this formula. So the max force, max friction is this mu s times Fn. And if I just do Newton's second law in this system, you'll get Fn equals W. I'm not going to go through that because it's trivial. Anyway, this is not always true. It's true for this case. So the max force is that number. And the numbers we have given here is 0.3 times 200 times gravity. Can somebody calculate and just figure that out real quick? If somebody can figure that out, just yell it out whenever you get that. 588. Okay, so this thing should be able to sustain 588 newtons of force, according to the numbers given. Let's see if that's the case. I think so, because 500 didn't work. Let's see what 600 did. We'll just try some. And I can also graph, so let's graph these forces. So on this graph here, I'll pause it. This blue line is the applied force. This red line is the friction force, and this green is total. The net force is 0, so it's not moving. Let's up this to like 550. This is not quite enough. The net force is still 0. If I go to 580, it still maxes. The force is still 0, so it's not going to move. If I go to like 600, notice now the net force is this much, and the friction force is dropped, and the applied force is more. So now the applied force overtakes the frictional force that's going to keep going. One thing I want you to notice is that at all these steps here, I increased the force and the frictional force matched it, but at some point when I overtook it, the frictional force suddenly dropped. And this is what Professor Moore was talking about in class today. He said that when you want to get something moving, it takes a little more force, but once you get it moving, the force to keep it moving is less than what it took to get it. So that's the next thing I want to say is that the max force to get something moving is this, but to keep it moving, once it begins, the frictional force, I should say once moving, once the object already starts moving, the frictional force equals this other kinetic friction times the normal force. And this mu case is usually a little smaller than mu s.
Did you always say that?
Yeah. Yeah, it's always a little smaller because it takes less force to keep it going than it does to get it. And I think for this guy, mu k is 0.2. So if you still have a calculator out, you want to calculate 0.2 times 200 times 9.8. I think that's like 300 something. What is 392? And I think that's the number up there. You see where it says red and negative 392? So it took about 580 to get it going, which is this one right here. Once it started moving, the frictional force dropped to the kinetic value, which is 392. And because I'm pushing with about 600 newtons, and the force opposing is only 392, it's going to continue moving and accelerating. So with that in mind, let's do some of these frictional formulas. So in chapter 6, we'll do this one yesterday. That's again, after 6 minutes. I did this one yesterday, so it's going to be a repeat for some of you who've already seen it. But I had to rush through it, so it's going to be a good review. The problem says there is a 2.5 kilogram block at rest on a horizontal surface. And there's a force pushing it with 6 newtons. There's also a vertical force pulling upwards. And it gives you the static and kinetic friction coefficients. Okay, the question says this. It says, determine the magnitude of the frictional force acting on the block if the magnitude of P is given by a couple different values. Let me write that here. So find the frictional force if P equals 8, 10, or 12. So we'll first do it for 8, and then we'll do 10 and 12. I want to find the frictional force, so let me just draw free body diagrams. Weight is down, normal force is up, there's also P up, and then there's a force pushing this way, and the force is pushing that way and it's not moving yet. So to keep it from not moving, the frictional force has to oppose it. So that tells you frictional force points back this way. Okay? Are there any questions on that?
Is that
How I do the vectors?
is that supposed to be F or P?
Yeah.
Oh, yeah. Okay. Are there any questions on this? Okay. So now the question says, what is the frictional force? I want to find F. So let me write down Newton's second law. And before I do that, I'm going to make sure I make my coordinate system. So in the x direction, I'm going to have F minus FF. That's positive, that's negative, and that's it. So that equals mass times acceleration. It's zero at rest, so its acceleration is 0. And then if I do the y coordinate, I'm going to have P plus Fn minus W. It's also 0, it's not going anywhere. And let's see what I know of this. I know W because I know its weight. I know F is 6 newtons. So I can find P.
No, we have P.
Oh, sorry. Okay, so I don't know P. No, I do know P. Sorry, P is 8.
You don't know Fn?
So I can actually find Fn. So we have the weight minus P. And this is, it's 2.5 kilograms times the acceleration of gravity minus P, which in this case is 8. You know what? I'm not going to set this equal to 0 yet. Yeah, this thing didn't say it was big enough, so I'm not going to set this equal to 0. Sorry. Let me just reiterate that. I should not have set that equal to 0 because the problem never said it wasn't moving. So I'm going to keep that little just open yet, right for right now. And then for the y, I know it's not moving up and down, so I'll set that equal to 0. When you solve this, you get Fn equals whatever this quantity is.
16.5.
16. Okay, that's the normal force. That's how much force that that the ground is sustaining. And the fact that somebody's pulling up on it means that you can change how much force is normal, how much force is sustaining. But because of the equation that relates friction and the normal force, it's going to affect the frictional force. So what we need to ask ourselves is, given this normal force, what's the maximum frictional force that this block can sustain? Well, we know that the max friction force, so this thing can prevent motion up to this value, to mu s times Fn. And mu s is 0.4. So the max force is going to be 0.4 times 16.5. 6.6, okay. So that's the max force it can sustain. So if you push it anything less than that, it's not going to move. Now, what are we pushing with? Pushing with 6. So that means that the frictional force, so F applied is less than the max friction. Which means that the frictional force has to equal the applied force. So frictional force equals 6. It does not equal that number. That's the max it can be. But it's telling me that it's not moving because it's not up to that. Because it's not moving, this equation is trivial. It's not moving, this tells me this has to be 0, so F equals Fn. So the frictional force has to oppose whatever you're pushing to keep it steady. And it'll continue to do that until it gets to that point. Until the frictional force is, until you push with at least 6 points. Is there any questions on the problem? Any stuff on the problem? Okay, so let's do part C then. Let's do part B also. Part B is the same thing, except you're going to change one of the numbers here. So everything here is the same, except now this number is 10, because I'm changing how much I'm pulling on it. So now I'm pulling with the higher force. So there's going to be less normal force. The friction it can sustain will be less. Because there's less normal force, the max friction will be smaller. So now this will be 14.5. So I subtracted 10 instead of 8. And that will affect this number. Should you have 5.6 or something?
5.8.
Still not good. Still not good. Is it? Maybe it is. Oh, it is. Sorry, yeah. The max that can sustain is only 5.8 newtons. So now, because you're above this force, you're pushing with 6 newtons, but the max friction is only 5.8, so this thing's actually going to start moving. But be careful, because once it starts moving, the friction force is not this. This just tells you if it does start moving. Once it starts moving, the actual force is given by the kinetic friction. So for part B, it does move. Because the applied force is greater than 5.8 newtons. So the frictional force, now that it's moving, equals the kinetic friction, the coefficient of kinetic friction times the normal force. And this is a different number because the kinetic friction is a little smaller. It's 0.25 times that. About 4 point something, 5? 3.6? Okay. So it took this much to get it going, but once it's going, this is the only force that's actually opposing it. All right. And then using that, you can find the accelerations. The acceleration would just be whatever works out of the formula. You have 6 minus 3.6 equals the mass times the acceleration. And you can solve for me. It's important to understand what's happening here because it's plugging in your numbers without thinking about whether or not